Hi, everyone. Welcome to our quarterly webinar. Luckily, we have Dr. Christopher Franck from Virginia Tech. We just saw him give a very nice talk at our Defense and Aerospace Test and Analysis workshop. We're going to have another one of these in September, another talk on Gaussian process modeling from our folks at Pacific Northwest Lab. I just wanted to give a plug for the SDNS at JSM. It's in DC this summer in person, and there will be invited talks, topic contributed sessions, roundtable. So be on the lookout in your email. There should be something coming out from either Carl Padzernik, our chair, or Justin Newcomer, our program chair, with the different days and the different sessions that we're sponsoring.
Great, yeah, so I'm Chris Franck here at Virginia Tech. What this course is a gentle introduction to concept use in Bayesian model selection and averaging. We're going to start with approximate methods based on the familiar Bayesian information criterion. So if you've been fitting statistical models in basically any software, you've probably at least heard of this thing. This is a good starting place to begin moving towards fully Bayesian methods. We're also going to have an overview of concepts and an open forum for questions and discussions. And we'll talk about some slides, and as soon as that gets boring, we'll maybe switch to an R demo at that point, and those materials are available on the seminar website, and I think they got sent out if you were registered by a certain time yesterday. So you can follow the slides along and the R demo along as you like. What this course isn't, we have 90 minutes, and not everybody's like intermediate to advanced, obviously. So I'm telling you right now, this is not like a fully described Bayesian approach to model averaging for categorical data. To do sort of the full version, you need to understand specialized knowledge in Bayesian modeling. You have to do the probability theory to mix prior distributions and likelihoods. And then in order to do inference, it's good to have familiarity with sampling, algorithms, and other sorts of things like that, which we just don't have time to cover all of that in enough depth. So I'll have plenty of references throughout the slides, but we're going to stop well short of going deep into that. Instead, the formulas I'll be presenting are focused mostly on this BIC approximation I described here. And just by way of background, like I said, I got my PhD in 2010, which is getting to be a while ago now. And I had like one course in Bayesian statistics, and I was interested in it. I wanted to learn more. And sort of this BIC approximation, it's close to my heart, because when I kind of found out about it and discovered it, I found that to be kind of a useful bridge to begin thinking about Bayesian ideas, especially as it pertains to model selection, and then onwards towards the more full Bayesian analyses, which I do more of these days. Some good news, if you're terribly disappointed by that, the really good news is we live in an era now where there's software packages that for certain Bayesian analyses are very good. So I'll be talking about the BAS package by Merlis Clyde. This basically, if you can specify like linear model syntax in R, this has a set of automatic priors you can use that produce well-calibrated, well-behaving Bayesian model selection and averaging. So we'll take the technician's view of that. We will see the full Bayesian machine in operation, but I will not go into all the details about that. For some references, and now I got like 3 slides of references at the end. This Liang et al. And Lee and Clyde paper in 2008 and 2018 talk about mixtures of G priors, which are very popular for linear models of different sorts. An automatic procedure, and then there's more about their algorithm that they use in that package is 2011. So you can check out those for more background knowledge if you'd like. So 3 parts. The first part is just a quick review of logistic regression, just to remind ourselves what that is. Then we will get into the idea of Bayesian model selection and averaging, which is a really cool idea that's very beautiful. In fact, like the excitement gets so high at this part of the lecture, it's hard to contain ourselves. And then we'll see an R demo that shows you how to do it, which is good. Now, unfortunately, like no statistical technique is perfect. We know that all of them have their drawbacks. And just as we get to this fever pitch of excitement about Bayesian model averaging, we will say a few things about it that perhaps aren't so good for all contexts. And we'll compare and contrast with another sort of approach called stacking. Or we're only going to very briefly mention that. Stacking is very useful to talk about at least a little bit, because it throws into sharp relief some drawbacks of model averaging, and it helps us think a little bit about our assumptions and things like that that aren't always totally realistic. So we'll come out of this with Fever pitch of excitement, it's more of like a tempered maturity by the time we're done. That's the goal here. So a brief review of logistic regression, just to get us into the mood. We're talking about this crab data from Alan Agreste's book. I'll give you some details on that in a minute or two if you're not familiar. But just by way of remembering what logistic regression is, I think it was Joe's idea to kind of extend the categorical modeling context from the short course I gave recently. So the basic idea of logistic regression is I've got a binary outcome. Here we're wondering whether or not crabs are likely to be successful at reproduction according to a certain measure. And this measure is binary. So 0 means no event, 1 means event. There's something like 173 data points on this plot. And basically we want a linear model because we know something like the size of the crab might have something to do with how effective they are ecologically. And the basic punchline of logistic regression is we fit a linear model on the log odds scale, which essentially produces things like this S-curve on the probability scale, which is why we like logistic regression. It allows us to consider binary events, which are very important, right? As a function of things we know affect the probability of those that are very well. It obeys 0-1 bounds in probability, which is nice. And logistic regression itself is a building block towards many other sophisticated modeling strategies as well. So even if what if I have 3 categories, or what if some assumption about logistic regression is not met? There are extensions of logistic regression for many different scenarios, making that just the natural starting point to use for this talk. So this is crab satellite data. Here's a picture of a horseshoe crab. Horseshoe crabs are interesting because they're living fossils. They've been around for millions and millions of years, much longer than other organisms. So I guess any organism that is that successful, maybe it's useful to study it ecologically. And you might think that perhaps one horseshoe crab is just as good as another, but the purpose of this data set really is to investigate whether that's true. These are, I took this from Alan Agreste's Introduction to Categorical Data Analysis book, and the binary measurement is whether or not a female horseshoe crab, while mating, has additional kind of male suitors, other potential mates in the vicinity, which would suggest that they have traits that are useful for reproduction. So the question really is as reproduction goes, what are the things that differentiate the appeal of different horseshoe crabs? The outcome's binary for these data. And the 4 candidate predictors we're going to be discussing are shell width, which is a measure of size, weight, the color of the shell, which is a proxy for age. Shell width, weight, and shell color are perhaps all proxies for age. You can't ask a crab how old it is, it can't tell you. And then spine condition, which I think has more to do with like the life experience and how rough of a time that crab's had. Of course, this is just a basic data set from a textbook, but you can imagine that you might have a modeling exercise where you're trying to classify different sorts of objects as a function of different sorts of inputs. And the techniques we're describing here could potentially be useful in that case as well. So just to finish up the notation, I've got this linear predictor, right? So I've got an intercept, I've got the shell width, the weight, the color, and the spine condition, and in different X variables, right? And I know that this line is unbounded, right? It could take any value. Pi of X is the probability of an event that depends on X. And of course, the probability of events between 0 and 1. Inside the parentheses, we have the odds. So the odds are between 0 and infinity, positive real line. And then the log of the odds are the entire real line. So this is logistic regression because this logit function maps the probability space onto the real line, where it can meet up very nicely with a linear predictor that's unbounded. Very cool. Y is binary, as we said. Beta not C intercept. Beta 1 to beta P are coefficients. Beta terms are unknown parameters. Like a beta term is like how important is a different predictor on the long odds scale. X1 to XP, I'm going to use this terminology. This is a little demo about model selection. So I'm going to call these candidate predictors because, perhaps not all of them should be in the model. Perhaps some of them are spurious. So a given model has all these X's, but we, in the broader activity, know maybe not all of these X's should be included in a final model. We want to assess that as part of the activity and weigh that properly. So just some basic logistic regression review there. And the dependent variable y here, the dependent variable is it's binary, and it's whether or not a female crab has additional male suitors and additional possible mates, yes or no, in their den in mating season. So it's more generally, the dependent variable here is a binary outcome, and we're modeling not the probability of the event, but the log odds of that event as a linear predictor of things that we think are associated with the event, which is a response to the question about the dependent variable, just something binary. Good questions. Although I ought to digress a little bit. Bayesian model selection, Bayesian model averaging, all these modeling concepts we're talking about today, we picked a categorical model just sort of as a use case for this demo, but basically all the stuff I'm talking about here works in other sorts of linear models as well, and other sorts of statistical models. These same sorts of activities might be of interest. So in fact, the BIC approximation works basically on any regular problem, and the BAS package, the BAS package, actually is usable for things that are categorical or continuous outcomes. So categorical outcome here, binary specifically, but the concepts are broader than just that, which is cool. So as you might know, probably everybody here has done some sort of model selection. It involves choosing the single kind of best model, and then all subsequent inferences based on that model. There's many ways to do it. When I was younger, we used to get our forward selection based on p-values. We would set our alpha to 0.05, and we would just kind of build up a model until p-values stopped coming in below alpha 0.05. That's how we used to do things. Whatever, there are other criteria as well that we're going to not necessarily talk about. But basically, however you choose your model, if you kind of follow this recipe in the first bullet point, an issue is you started the game by saying, I'm uncertain what model is to be chosen. And then maybe you pick a model that's only slightly better than the second best model. Then you pretend that is the true model that generated the data. And then you do all of your inference based on that model as if you knew in advance it was true. That kind of understates uncertainty in the model selection process that perhaps should be carried forward into inference, which is one of the things that model averaging helps with. But again, just as we're coming up with these terms, model selection just says, give me the most probable model, pick that. Give me the lowest BIC or the lowest AIC or the best CP statistic, whatever your preference is. If you just do that, that's model selection. In this case, we have only 4 variables, so we're going to do an exhaustive search, 2 to the p possible models. So there's 4 possible predictors here, so 2, 4, 8, 16 models in the crab example. That's no problem. 16 models is easy to fit, but of course we notice the model space grows exponentially with a number of new predictors, which is a bit of a problem. So in addition to the issue with model selection, ignoring uncertainty in the model selection process for subsequent inference, in realistic problems bigger than what we find in a typical textbook exercise, you could have p very large, right? If it's going to double every time, it can only double so many times before you're not really going to be trying to fit every single model to get BIC or something. The good news is there are algorithms that themselves search large model spaces. Markov chain model composition and genetic algorithms and other sorts of things can kind of search the model space sensibly. So large P here is a challenge, perhaps, but it doesn't mean you can't do it, which is something. I like this. Hooding et al. Reference 1999 is a tutorial on Bayesian model averaging, where they describe some of those algorithms in terms that are very easy to grasp what's going on. So that's a good starting point if you're interested in these ideas, but your P is very big and you're not going to really visit every single model. That would be a good paper to look at. In terms of plotting some data, let's just kind of, I had a professor back in the day who always said the first rule is plot your data. I think that's pretty sensible. So here are 4 plots that just kind of look at the binary outcome as a function of each predictor individually. Here, it looks to me like if the female crab is wider, perhaps it's more likely she has multiple possible mates, right? Width is going up, more dots in the yes category there. For weight, it looks kind of like that's true. I mean, there was one really heavy crab in the data, right? I think the data are well vetted. They're in a famous textbook, but this could be, this point is certainly kind of remote in X, but there you are. That's what the data look like. Shell color. So the idea is that shell color goes along with age a little bit, and perhaps that is something that has some information. Medium light, medium dark, and dark. I always appreciate moments like this because it makes me realize somebody like went out onto the beach and gathered 173 crabs and had a color chart, and they color labeled every single one of them. So these are not big data, but it sounds like they were not necessarily easy to get. And then spine condition. These are labeled as like low, middle, or like bad, middle, good. Which I guess is a similar thing. The ecologists examined the crab and determined what condition the spine was in. Shell color and spine here are ordinal, right? And then the other two are continuous predictors. This is a group, I think, with a good statistics background. So sometimes I try to present this as like a riddle for undergraduates, and it vexes them. But I think most of us here know if the X variables are associated with each other, that could have consequences for the analysis. If we were merely modeling, width and weight both as predictors in the same model, we can see that these are highly collinear, as you'd expect. They're both measures of size. And that we know that, like, for usual statistical modeling, if I incorporate both of those in there, the symptom we see in our output is much bigger standard errors when they both appear versus the relatively smaller standard errors if only one appears. So in addition to the fact we have 4 candidate variables, we have 16 models, and we know in most realistic situations, these X's themselves may have some dependency, and that could have consequences for the analysis. So we're going to have to think about that as the analysis proceeds, and maybe during the live coding session, time allowing, we can look at some ways of trying to understand what consequence that'll have for model averaging. And then, like I said, this is sort of a formal slide in case I'd forgotten to mention that logistic regression is like a starting point as a building block as a categorical model. I really like this table. It's from the same book that I got the data set from. I use this to teach undergrad statistics, which is really cool. And it just reminds us that you could have all different sorts of explanatory variables, continuous, categorical, mixed. You could have different type outcomes, could be normally distributed, binomial, multinomial, Poisson, or more generally count-based. And we have names for all these different models, but they're basically all different types of generalized linear models, is usually the starting point here. And everything I'm saying about model selection and BIC and that sort of thing kind of works fairly well, would extend well to anything on this slide for sure, which is just a nice reminder. I'm not teaching you something that only works for logistic regression problems, and then like for the next type of models we have to start all over and reconceptualize everything. Again, just using logistic regression as a starting ground. Another just caveat, 2 of these predictors are nominal but categorical, right? So shell color has 4 categories, spine condition has 3 categories. I think most folks here probably know. I can elaborate on a little bit if there's interest. For categorical predictors in linear models, typically the way you do it is you introduce an array of zeros and ones into your X matrix. You basically come up with a bunch of dummy columns in your X's that give you different effects for each of the different levels of the categorical predictor, right? And that's just like a pretty standard linear modeling strategy. For this demonstration, just because we're really focusing on the Bayesian part, this came up in another seminar I gave, and it's a totally valid point. These 2 nominal variables, color and spine, you could handle them in this manner, no problem. In the live coding session, we can maybe try to back into that. But the analyses in the book justify treating these as linear trends. So just to kind of keep the focus on the main part of model selection and model averaging, I'm treating these as the linear trend on the log odd scale of the event, and not formally as a categorical predictor with, in this case, it would be like 3 degrees of freedom for color and 2 degrees of freedom for spine. That's a bit of an extension of what I'm doing. And if you check out the book and if you do some basic analyses, the linear trend does a pretty good job describing the data. One could argue that even if it does, you should still use a categorical predictor, and that's a reasonable opinion. So this is just a disclaimer that I'm treating them as linear trends for the next hour or so. So that's a background of the data set we're talking about. It's a background of logistic regression and kind of the modeling framework. Now the question comes into Bayesian model selection and averaging, which is really cool. Now, a couple of different things. this is the dangerous part of the talk, where we're going to begin moving into some formulas. We've already been going for about 25 minutes, and it gets a little harder to see the forest for the trees. So what I'm going to do is I'm going to show you some formulas. I'm going to tell you where they come from. You probably, if this is the first time you're seeing them, you might need to stare at them a little bit in the slides later to really grasp what's going on. But you'll see the formulas. I'll give you the justification for what they are and why they work. Then we're going to see the formulas implemented in a live R demo, so you can see what would somebody actually do with these formulas. And then I'm going to take this technician's view and use the BAS package to do the fully Bayesian analysis, which is going to corroborate what the implementation of the formulas say. So we're going to kind of use a trusted package to back into some of the same quantities, just to convince ourselves everything is working well and that what we think we've learned is indeed valid. So again, I'll be presenting several slides of formulas now. I'll be describing the rationale for them mostly. You can check them out a little bit later. We'll see them in a live demo, and then we're going to use a software package to kind of make sure everything worked out the way we had hoped. And after formulas, then our demo time. So that'll be fun. Basically, for a set of candidate models, as we said, there's 2 to the P models, right? There's every possible combination of variables. So every predictor variable can be either in or out, right? So there's in or out for the first one, 2 times 2, if you have 2 candidate predictors, then 2 cubed for 3, we're up to 2 to the 4 here for 16. So the number of candidate models doubles every time you introduce a predictor. You include the intercept in every model unless you have good scientific reason not to. In other words, you know what the log odds would be at certain values of X, maybe then you could take it out, but in typical practice, you would leave your intercept in the model for sure. Notationally, I'm going to use this M sub K for K equals 1 to big K. That'll refer to a model, which in this case is just a collection of candidate variables, candidate predictors. And for the Bayesian model selection and averaging, each model requires a prior probability, right? So in this case, we have 16 competing models. We could call an ecologist on the phone and ask them what they think and try to do what's called subjective elicitation, right? So there is the activity in subjective Bayes where you get experts on the phone or the Zoom, I guess, in this era, and you try to get their information and formally incorporate it in your prior. And that entire exercise is called subjective elicitation. There's been a lot written on that. But for now, let's just put a uniform prior. I don't know what model we can do. There's 16 of them. For now, let's put 1/16 probability on each model as the prior. We can play with that later if we want to. There's a great paper on specification of model priors, Scott and Berger 2010. They talk about how to induce multiplicity adjustments and then just kind of review like this important step of prior specification, some drawbacks with what we're doing, the uniform prior. So that's a great paper to check out if you're thinking about priors on the model space and what you can do with those. But for us, 1/16 for every model. That'll be our prior. Bayesian information criterion, I think this is well known. Hopefully you've heard of it before. If not, this is probably the coolest thing I'll teach you today. A well-known approach to model selection is you compute what's known as information criteria. So you've probably heard of AIC, BIC. There's many different extensions of them for each of the models. You can compute your information criterion, and then you get whichever model has the lowest criterion. You use that model. Now you've done model selection using an information criterion. It's sort of known, AIC was the original article, but it's known that it picks models that are too big. But BIC is model selection consistent for regular problems, meaning if you actually have the true model in your candidate set, more on that later, and you increase the sample size, BIC will increasingly put posterior probability on the correct model, that's why we're talking about that today rather than something else because of that property. Like most criteria, information criteria, BIC has a term that rewards high likelihood and penalizes complexity, which is the number of parameters. So here's the formula that you have maybe seen before. BIC for the kth model, it's -2 times the maximized log likelihood. Oh, I forgot to put the penalty term in here. That was a rookie mistake. Plus P times log of n is the penalty for, so I should say plus P log n here, which is the penalty for the number of parameters. My mistake. But a good thing to remember is, especially for those who are trying to figure out how to do more Bayesian statistics, and all it seems like you have are individual papers that are very hard to read and textbooks that are also hard to read and kind of long. How do you kind of break in? Something cool about this Bayesian information criterion is it's going to give us approximate Bayesian model selection, and you can very easily get it out from any software like R or SAS or whatever you like. You can get it from that very easily. So very easy to get, and it's going to kind of be our gateway into doing some approximate Bayesian model selection and some reasoning. Cool. Formulas time. So the point of this slide is there's a certain quantity called the integrated likelihood, right? And the idea is, in our case, we have 16 models. Some have only 2 parameters. Some of them have 5 parameters. They all have different numbers of parameters. I like to think of this as let's think of the integrated likelihood as get everything onto a single metric, regardless of different numbers and roles of different parameters and different candidate models. And basically, you get this thing by multiplying your this is kind of the Bayesian notation for likelihood. Multiply it times your prior for the parameters for each model, then integrate the parameters out. So you've basically, since this is the Bayesian approach, we're treating potentially the data and definitely the parameters as random variables. We're forming their joint distribution. We're integrating the parameters out. That gives us what's known as the integrated likelihood. The good news for us here is there's a lot of complexity here. It's delicate trying to compute these, and it's even more delicate choosing what the priors on the parameters should be, right? So there's this great, this is an archive article called Cake Priors, and among other things, this article has a really good review of the history of problems choosing. You would think that the prior on the parameter should affect the posterior model probability. It turns out priors on the parameters play an outsized role. So this is kind of like a big rabbit hole of its own to really handle this with care. So I think we should just have an approximate that we can use an approximate approach based on BIC that kind of sidesteps the need to compute this integrated likelihood, which is nice. Also, even if you're really good at calculus, for lots of models, you can't just sit down and analytically do this integral. You have to rely to some numerical approximation or sampling algorithm in order to get it. So it's not easy to get, and if you made a bad choice about your priors, you're going to get something really bad, right? So that's the story there. So we want to avoid any problems that come out of that, right? So I'm gonna come back around to how we're going to get this in a minute, but supposing you have your integrated likelihoods for 2 models, perhaps you heard of something called a Bayes factor. And the Bayes factor is basically just the ratio of 2 integrated likelihoods for 2 competing models. So I could have like the width only model maybe is my MJ, and this is the integrated likelihood for that. So if that's high, that model has support. And then maybe this is the ratio where maybe I have 2 predictors in this model. And then like the Bayes factor being high favors the model on top. Bayes factor being low favors the model on bottom. That's the way sometimes you think about it, but more formally, the Bayes factor, it's a quantity by which data update prior odds to posterior odds. So this Levine and Skirvish paper, Bayes factors, what they are and what they are not, from 1999. I think it's in the American Statistician, very readable. If you want to know more about Bayes factors, you could check that out. But basically, what you can think of is a high Bayes factor above 1. The higher it is, the more it updates your prior towards model J. If it's below 1, it updates your prior towards model K, which is nice. This is for 2 models. For a BIC approach, access to Bayes factors, that's kind of an intermediate step. And kind of here's where some of the magic comes together, right? This is something that has been well known for people studying this since at least the mid-90s, maybe earlier, right? But basically, what this simple formula is telling us is I can get the BIC for any 2 models from my software. I can take their difference, multiply it in half, give it a negative sign, and exponentiate that. And that is an approximation of a Bayes factor between those 2 things. So basically, to walk this thing forward, like into the more of the rationale of why these formulas today, you can take BIC that you can fit from competing models today and approximate a Bayes factor from them, which is I've in the last decade I've been kind of surprised to learn it, and especially not how well known it is. For example, let's do another thing. Who here before today, reach for your reactions, has like heard of BIC sometime? So if you've heard of BIC before, give me a thumbs up. Lots, like everybody's heard of BIC, right? I mean, not everybody, but a lot of people had heard of BIC. I personally didn't really even see this approximation until much later. I knew about BIC from my textbooks, and I picked many models with low BIC, but I didn't realize this approximation basically towards a Bayes factor was a consequence of having BIC. So I think the number of people who know about BIC is much greater than the number of people who think BIC, or who know about this result. BIC can be used in this way, which is really very cool. So basically now we're seeing the first sort of basic idea feeding its way into some of these perhaps less familiar formulas for Bayesian model selection. This would handle, if we only had 2 models, we might like a Bayes factor, but of course we have 16 models. So if I want, what I really am going to need to proceed with this is going to help me explain what I've learned to my client. I'd like to have the posterior model probability of every prior. So this is saying the probability of model K given the data. This is called the posterior probability of model K, because I'm conditioning on the observed data. And all it is it's a straightforward application of Bayes' rule. It's the likelihood for model K, the integrated likelihood, times the prior for model K. We're just doing 1/16 for today, over the sum of all those things. That's just Bayes' rule. Very cool. So what we're kind of seeing here is I'm seeing some integrated likelihoods in ratios with other terms that are like integrated likelihoods. And like right now, if you're thinking to yourself, I bet I can just use algebra and get out of this, then like your middle school and high school algebra teachers they suddenly, the hair on their neck is standing up and they're very proud of you, because the great news is this kind of key quantity, the posterior model probability, really can, if you take the other result I gave you, I'm going to scroll up in the slide. If you take this basic result to get a bunch of Bayes factors with reference to a single model, I can use algebra to back into all of the posterior model probabilities, which is really cool. And I'm not going to carry that exercise out now, but basically the way it proceeds is you set one of your models as baseline, and it doesn't really matter which one. I approximate my, if you look where my mouse pointer is going right now, I approximate the Bayes factor for model K to my baseline model 1 using BIC. So that was super easy to get, by the way, right? That was easy to get because I know how to get BIC. These are easy to get because I get to pick them, and I picked for now 1/16 for both of them. So this actually cancels under a uniform prior, but it's easy to compute either way. And then the really kind of cool thing is, without loss of generality, I need to just appeal to one formula on the next slide. You can get the baseline model basically by, again, just taking using algebra and solving for the formulas. You can take the ratio of these priors times BF to K to 1, sum all that thing up and invert it. Now you've got the posterior model probability for your baseline model. You feed that back in, and you get the posterior model probabilities for all of your models. The main purpose of the talk is Bayesian model averaging, right? So we've gotten to the point where we know in a minute we're going to see in the R demo how to do this BIC-based Bayesian model selection. But I think everybody really came here today because out of these 16 candidate models, maybe we want to average the models together in a sensible way to get a really good guess as to what the outcome should be, to understand its uncertainty more specifically in terms of all of the candidate models. So for any quantity of interest, this triangle is a capital delta. For example, you might be interested in the parameter value. Like if you're studying something and you really want to understand how important is a parameter, what's its posterior distribution, given all the other parameters being able to be in the field of the candidate models, you might be interested in parameter value, or you might just be wondering what variables can I drop out. Something really kind of cool is you can just use this law of total probability. And we've got, this is just like from your probability theory class. We're assuming that the candidate models form a partition, more on that assumption in a little bit. But basically, if I take the probability, if I take the posterior of my quantity of interest, given the model and the data, times the prior on the model, I'm sorry, the posterior model probability, which we just got, add them all up, that gives me the posterior for the quantity of interest. So here's the key point in English. Whatever it is you care about, right? I got something, I care about it so much, I sent 200 ecologists on the beach to measure horseshoe crabs. They gathered all this data. I really want to know about something about that. I know I've got at least 16 models that I want to leverage all of them appropriately. And anything I care about in that framework, what this formula is telling me is I can use the posterior model probabilities as weights and essentially build a weighted average using also the posterior, the thing I care about, across all the models. And now that's basically the justification for why Bayesian model averaging works, which is really cool. So another way to say that is, if you go through all the effort of setting up Bayesian model selection, you can do Bayesian model averaging just very easily beyond that, because you use those posterior model probabilities as weights with the law of total probability to get a posterior on anything you care about in the context of the entire model space. Very cool. Lots of times we just want to know what's the probability that, for example, shell color, that the beta term for some predictor, maybe shell width, is 0. You can get posterior inclusion probabilities, which measure the probability that a candidate predictor is in the model or not in the model, right? The cool thing is that you can basically just treat delta as an indicator variable, and then you can re-express your Bayesian model averaging equation from the previous slide, and you can easily get posterior inclusion probabilities just like that. So what we're going to do is we're going to move into an R demo. Here's the scope. I'm going to manually implement this BIC approximation, right? So there'll be things that look quite familiar and maybe some things that look a little new. I'm going to basically move from BICs to posterior model probabilities and inclusion probabilities that quickly, which will be cool. And then that's a technique you can use on your own model averaging problems. Further, I'm going to demonstrate, like I said, I'm reminding you here. Oh, I got a chat. Is there a way to apply this method for a machine learning model like a random forest? Ooh, that's a really good question. Is there a way to apply, I'm going to repeat the question from the chat. Is there a way to apply this method for a machine learning model like random forest? I would say, I mean, a random forest itself is sort of a collection of predictions from different trees. If you have lots of predictions from different sorts of algorithms, right? So suppose rather than having a crab with different predictors, imagine we have some sort of categorical outcome, and I have multiple machine learning predictions for that outcome. One of them might be random forests, one of them might be something else, some of them might be probabilistic scale, some of them might be like a confidence score. You could treat those inputs as predictors in a logistic regression and model average on top of that if you want. I'm not saying you definitely would want to do that. I'm not saying that's definitely the best way to go, but the answer to the literal question, could I take a bunch of machine learning predictions and then do another layer of Bayesian model averaging on top of that if I had the outcomes? The answer to that question is yes. I first used this BIC approximation in this context in a behavioral economics project, which is kind of fun. And then later I got more into the fully Bayesian approaches, and they're really cool too. So all the techniques here I think can be used in practice if used carefully. They are like publication grade techniques useful for analyzing data. Got another chat. Do we need to adjust for uncertainty in the Bayes factor? That's a nuanced question, right? So basically a Bayes factor is what you end up doing is you come up with some way of getting an integrated likelihood under two different models, and you take the ratio, and then you just plug the data. This is what everybody does, right? You just plug the data into the observed data into that strategy to get a Bayes factor. And of course, the Bayes, so this is a deep question, and I love it. The Bayes factor is a statistic, right? And statistics themselves do have uncertainty. They do have standard errors. They have distributions, right? So I definitely appreciate if we had collected different data from the same mechanism, I'd have gotten a different Bayes factor. But at the same time, I haven't seen much effort where people consider distributions of Bayes factors directly. Most of the stuff I see, people just plug in the observed data. And there is the concern about whether the Bayes factors are or aren't stable if you sample different data from the same process. Do we need to adjust for uncertainty in Bayes factor? I don't think you literally need to. I don't see it that often, but I can appreciate the argument that it must be there. Yeah. Here's another question. Can we include interaction terms in the model? Then the total number of models is more than 2 to the p. Yeah, definitely. In fact, you can absolutely put interaction terms in the model. Recently, I did this for a biomechanics kind of quick data analysis where we were using these sorts of techniques, and we actually did include two-way interactions. No problem. Here's the good news. A two-way interaction, a three-way interaction, any number of interactions that you have. Oh, by the way, I'm just reading out loud. This was sent to me as a direct message. Okay, so I don't know if everybody can see this. So let me repeat the question again. Can we include interaction terms in the model? Then the total number of models is more than 2 to the p. That's the question. The answer is definitely. The good news is a model with interaction terms is just a model with a different X matrix, but it's in the same class of models, different number of parameters, so P is different. And the number of candidate models is different too, but you could do that no problem. Great question. Okay, I think I've answered all current questions. Now let's go in here to the R demo. You could do this in Python, you could do this in whatever software you want. Here's R. This is the demo that I sent out. I'm reading this Krabs data. Every time I read it in, I click on this to make sure it does what I think it did. Yep, I got weight, width, color, spine. Y is 0 and 1. The number of satellites, if you want to treat this as a count-based regression, that's in the data. You could use that as well. And then an index number for Crab if you need it. It's there. So the data came in fine, 173 observations. That looks fine. Basically, the first several slides, I'm just kind of showing you how I got the plots from the presentation, right? I just fit a GLM here and I predicted the S curve and I joined it together. This is just to kind of tie this to the slides a little better. I coded it up for the slides anyways. Here's how I got the plots for the data. We've seen this before. By the way, I didn't really make a big story out of this, but I jitter the data a little bit, right? Like if you don't, especially here, like if you don't jittering, you add a small amount of random noise to each data point to unstack stacked points. If you don't do this, then all 173 observations look like just like 8 dots on a plot, and it doesn't help you very much. So the reason that I'm saying these are binary and categorical, binary Y and some categorical X's, but it doesn't look that way is I've jittered it. I've added a small amount of random noise. Useful visualization technique for categorical data. And then similarly, here's the scatter plot matrix. We know multicollinearity is in there. Cool. Okay, so first order of business. I am going to, upon request, go back to the slides. During rehearsal, I asked myself, should I flash back and forth to the slides after every line of code to show what formula that line of code did? Or should I just go through the demo and try to say that this was in the slides and look back later? And it just got to be chaotic when I kept flashing back and forth. So if you'd like me to try to tie explicitly lines of code to the slides, send me a note. I'm happy to do it. But as it stands, I'm going to just execute the stuff from the slides, the formulas, and you can tell me if you want further detail from that. So that's the story there. Basically, I need the BIC for all 16 models. So I could fit all of them manually and then use the BIC command to get them. Instead, I'm going to use this best GLM package. So if you Google model selection in R with GLMs, generalized linear models, that is, this is best subset selection for information criterion or cross-validation. The long story short is you put in your X matrix appended with your Y vector. I'm going to say the family is binomial, what information criterion I want, and then it's going to do it for this class of models. It'll do exhaustive search. So basically, I'm using the best GLM package here just to get a vector of BICs, right? And the corresponding array of input variables that are inside in the model or not. That's all I'm using it for. So I create this XY matrix, which best GLM requires. And then again here, I'm just saying, give me all the models, which is cool. This Morgan Tadar search, since family is non-Gaussian, that just means search all the models. Now I've got a little comment here. I know there should be 16 models. I don't know if this was a feature or a bug. The top models, it only gives you 15, even if you ask for 16, right? So basically what I'm doing is if you if you run this code, you'll see that you can get the this code in the comment here returns what the 16th row should be, this 230.776 for a model. The worst model of them all that has only spine in there is it not included in the 15 top models. So I'm just manually reintroducing it. So that's a little bit of a hack. But basically at the end of the day, what I've got now is weight, width, color, spine. Each row is a model, right? So 0 means that term was not in there. 1 means it was. And then criterion is BIC. Low BIC is good. So before today, if someone had given you a question, what single model might I pick for this crab data, for the satellite data? You might have said, well, the model that has linear predictor of width and color has the lowest BIC. So by that reasoning, maybe we should pick that model, and then with all the other caveats as well that go along with statistical modeling. Now that thing is off. Listen. But look, these are pretty darn close BIC values, right? Like this second model, this is something I think people's eyes kind of gloss over. We're going to solve this in a minute. Like, is BIC 199.43 that much better than 199.6, right? Like BIC is essentially on a likelihood scale where some penalty has been induced based on sample size and number of parameters. One thing that's really cool is what we're going to do now is we're going to see what the posterior model probabilities of those are, right? This just confirms for me this 0, 1, 2, 3, 4. This is how many terms are in the model, how many models have that many terms. So there's intercept only is the only model that doesn't have any coefficients. If a model has all 4 coefficients, there's only one way to do that. And then with combinatorics, there's 4 ways to get 1 predictor out of 4 candidate predictors, 6 to get 2, 4 to get 3. This is just confirming that the 16 models do have the right number of predictors, right? Cool. So up to this point, we now have this nice array of BIC values, which we said were the core input to our model selection and averaging approach. And I've got this form. Now is the point where I go into the formulas here. So I'm taking the vector of BICs, right? I'm declaring the first model to be the baseline. That's model 1 from the slides. I'm getting all of the Bayes factors relative to the first model. So I'm exponentiating the half difference between each term in the BIC vector and the baseline BIC, right? So the thing that I paused on, it was the slide with just that one small formula. And I said, not too many people know about this, surprisingly, even though everybody knows about BIC. This is that formula, right? And if I chose to look at it, I would see, of course, the Bayes factor comparing the baseline model to itself is 1. And then I've got Bayes factors comparing, approximate Bayes factors, comparing every model to the baseline model. I've got this uniform model on the prior on the model space. So if you hated that idea, then this would be the line of code you'd want to change. I'm making my model priors prior probabilities 1/16 for all the models. The first one's the baseline prior. And then you do some algebra on a couple sheets of notebook paper, and you come up with the formulas from the slide, and you put this like this. And at the end of the day, you end up with this model frame, which is this which I'll just show it to you. All I've really done now is I've appended the array of candidate predictors and BICs with the posterior model probability based on the BIC approximation. So check this out. Like, to my question, is it really that much better to have a BIC of 199.43 than 199.6? No, right? And also for an exercise like this, the posterior model probability that this is the true model is like 27%, right? The next best one is like 25%. So something to bear in mind in practice when you just do model selection. There's many reasons to like model selection. There's many reasons to be worried. Here's a reason to be worried. Lots of times you run away as if you have this all-star model that like won the day, and then you go forward as if that's the true state of the universe. But lots of times the second best model, especially for lower sample sizes, is really darn close, right? You're basically just as well off. So one good thing about these posterior model probabilities is they show in a way that's more interpretable than the BIC scale how close these models are. The third one only has like a 15% chance, 13, and then all the way down. No more posterior model probability after that. These things sum to 1, which is cool too. So I've basically now got posterior model probabilities for all the models. Oh, is Chris Saunders? Oh, he's hey Chris, how you doing? Is BIC consistent for selecting between different numbers of components for mixture models? No, that's so for mixture models, very briefly, I carefully said BIC works well for regular problems, and then I didn't say another word about that. Chris Saunders is asking a question that kind of relates directly to this. For lots of as statisticians, we get immense comfort when, if I make the sample size bigger and bigger and bigger, I get closer and closer and closer to the truth, and my precision gets tighter and tighter and tighter. Like, we just sleep easy at night as statisticians if that's true, right? So that's an asymptotic argument, and different sorts of statistical techniques, whether it's a likelihood ratio test or likelihood-based information criteria, they have certain assumptions that are required for those asymptotics to behave properly, right? So when I say a regular problem, and those are sophisticated mathematical things, but one of the ones that gets broken a lot is a problem is said to be like irregular if I can set if some values on the boundary of the parameter space elicit other models in the set. So for mixture models, in case you don't know, if you think of like a sum of weighted components, densities, I can set some of those weights to 0 to get smaller models. Therefore, there's like a boundary, the boundary of the parameter space. If you go to that boundary, then you've got a model there. And things like likelihood ratio tests and BIC don't work as well as they do if you're in a situation like we are, where 0, the null value of 0 for a regression coefficient, is not on the boundary of the parameter space. So there's a bunch of work on this dating. In fact, I don't know if what was it, 2007, I had to write a little written prelim paper for graduate school about this problem. And people use BIC. You can compute BIC and use it for this purpose, but you're not guaranteed to get the right number of components as the sample size goes up. BIC doesn't nail it in general. DIC, the deviance of information criterion, doesn't either. And that's just because of irregular asymptotics. So the short version of that is there are examples of problems where the BIC approximation is not model selection consistent, and you could jack up your sample size and still not get the right answer. Does that answer the question? Great. Cool. Now we'll just look at some posterior inclusion probabilities. I'm using the posterior model probabilities as weights, and basically, if you look at that formula, you'll realize if I want to know the posterior probability that shell width is in the model, I can just add up all the posterior model probabilities that have shell width in there. That's what this next chunk of R code does. And the cool kind of thing like this, I'm just going to run it all in one go. This is something that kind of comes out that's useful for summarize. Like, you can't easily get this without further analyses or ad hoc analyses out of a single model. Because what this is saying is, with respect to the entire set of candidate models, the probability that width is non-zero is like 65%, something like that, right? Weight, less than 50% chance that it's non-null. So high here, this is the probability the thing has a non-zero effect across all 16 models. So spine doesn't look that impressive. Color, yeah, just barely above 50%. Width is a little bit higher than that. Weight is kind of low. And this is a posterior inclusion probability, which is a very useful plot to summarize the plausibility of an effect. Not just, like, for example, why is this plot good? If we just did model selection, I would conclude, well, width and color are in, and weight and spine are out. And then someone would say, but if I look at the plot of weight with the outcome, it looks like weight has an effect, right? What this is doing is it's giving us a more nuanced look. It's telling us the probability of a term being non-null. That's what an inclusion probability is, rather than just forcing us to say something's in the model or out of the model, which isn't as realistic. So for that reason, people like these posterior inclusion probabilities. Cool. As I promised, technicians view this BAS package. You can just get that. I'm going to update that package. It's going to do its thing. call it up. And this is pretty cool. I'm saying bas.glm, y is distributed, this dot means give me everything in the thing. Number of models is 16. The data, or these columns of the crabs data. This method uses MCMC in order to do model selection, which I haven't talked about. So again, we're using now a different method to compare with the BIC approximation. This beta prior, BIC prior, to the best of my understanding from a reading of the documentation, this is it's a fully Bayesian analysis, but it adopts a prior like the prior that BIC implicitly uses, and people were studying what that prior is in the mid-90s. Families binomial, model prior is uniform. So basically, this is like a fully Bayesian variant of the model selection and averaging I've talked to you so far. It went that quick because we only got 16 models. And it gives you 4 descriptive plots. I'm going to kind of move through this a little quickly, just to leave time for questions. But what this gives us is some residual versus fitted values. This is cumulative posterior model probabilities. That's why it goes all the way up to 1. Model complexity. This is the number of terms in there. And then the log of what it's calling marginal is what I'm calling the integrated likelihood. Basically, the moderate sized models have the best integrated likelihoods, in case you're interested in that. And then kind of something that just helps us feel good. These inclusion probabilities comes right out of the package. Intercept is definitely in because we always leave that in. And then these weights, widths, and colors, you can see that what this fully Bayesian version gave us. So the BIC thing that I talked about with the formulas is an approximate solution. Here's a fully Bayesian approach that is approximate because I ran MCMC. But what we're going to basically see if we look at these, I'm now pulling the inclusion probabilities from both. And they're not in the same order, but you can see like width had a 68% probability according to both of them, basically, and then 41. So it's all matching up. So that's always reassuring. I didn't just make up some crazy, stuff about BIC secretly being a good approximate version of Bayesian model selection. That's all in the literature. You can check out the papers. And indeed, you go to run a fully Bayesian analysis, and it corroborates all of the results from the formulas, which is just nice. Also, we didn't make any silly mistakes that would have broken everything. So that's really cool there. One thing that people like about averaging, I think I put in the slides, but Bayesian model averaging can do better than an individual model. Otherwise, we wouldn't do it. So I'm getting model average predictions. I'm just comparing like the different sorts of fits here. So the simple logistic regressions prediction, it looks like it's close to the model averaged prediction. The highest probability models prediction also looks close. I didn't run one of my lines of code here. There we go. Just as a quick look, this is called a point. I'm just having a quick look at, are my model predictions really associated with the outcomes in my data? In real life, by the way, we probably should be using cross-validation, right? So if we have more than 90 minutes to develop things and do demos and stuff, we probably would have held out some of the data, and we really would have judged different models and model averaging approaches based on how well they predict out of sample data. I'm doing a simpler version of that, and I'm just looking at within the data, the correlation between the outcome, which is binary, and the predictions, which are continuous. That's known as a point biserial correlation. And you can say, what am I doing here? There. Oh, this BAS, I changed the name to BMA. That's what I did. My bad. So what this is showing is that the best model, or the model average, the correlation between the model average prediction and the actual data is 0.44. Correlation between the best model and the model average predictions also 0.44. And if you just go with a simple logistic regression model from the S curve off like the first slide, that thing doesn't do quite as well. So just look at that. You might be wondering, oh, wow, now that I got this BIC thing, why don't I just use this forever? Why do I need a fully Bayesian thing? Let me take 1 minute and show you this. What I'm going to examine now is the I'm sorry, I was not careful while renaming some of these in the 11th hour producing the demo. What I'm going to do now is I'm going to show you the posterior distribution of all the coefficients. So very briefly, we're talking about Bayesian statistics, but the emphasis so far has been to talk about the posterior probability of competing models. Of course, the Bayesian paradigm is much bigger than just that. And in general, Bayesian statisticians, they have a prior belief. They take a likelihood, they combine it with a prior, they get a posterior, and then all inferences based on the posterior. That goes for model selection if you're into that kind of thing. Not everybody is. It also goes for the parameters themselves. So you might be wondering, Chris, how do I get good Bayesian posteriors for my coefficients so I can actually go back to the ecologists and tell them the model averaged effects of these sorts of things? The very wonderful news is this BAS package has that built in. This is the posterior distribution of the intercept. So if you wanted a 95% credible interval, equal tailed, you could just move in 2.5% on that sides of this, and then you'd get your intercept interval that way. This is bimodal because obviously if the intercept is the only term, then the rate is different. As we know from logistic regression, by the way, if you don't have any terms in there, the intercept is the log odds of the event. And if you have terms, the intercept moves a lot. So this is bimodal because there's one intercept only model and then many models that have similar intercepts that have other terms. That's why this is bimodal. Makes perfect sense. Here's the posterior for weight. By the way, there's a 40-something% inclusion probability of weight, meaning there's a 60% chance that weight doesn't come into the model. And then there's a 40%, the other, so this itself is a mixture model or a mixture where you've got your posterior's got a point mass at 0 corresponding to the null state, and then a posterior where 40% of the mass is there. So you can get your credible intervals that way if you want. Same for width, right? These are both positively associated with satellites, and then for color as well. So and spine as well. So the really cool thing is we live in a good era where for models like these, we have a software that does a fairly safe, fully Bayesian version as well. So that's just a little bit of motivation more towards what a fully Bayesian analysis can give you that the BIC approximation alone does not naturally give you. Question from I got a couple questions. Was color significant in model 1? Color is not an impressive predictor. Let's go back to the slides. Was color, okay, I think I see the question now. Was color included in the very best? Yes. So I'm answering Christopher Morell's question now. Thank you for the question. Color is in the very first model. So is it weird that it's in the very first model and yet it seems kind of equivocal on the back end as to whether it is impactful? But the best model only has 27% probability, 28%, right? And then we're not going to see color reappear until the models have like 4% probability. So there's this it appears like a paradox initially, an unimpressive variable is in the top model, right? But then its posterior inclusion probability and its posterior distribution of its coefficient seem very equivocal. Well, yeah, because the top model didn't win by all that much in this case, and many other well-performing models didn't have color. Does that answer the question?
Yeah, was its p-value significant if we use the sort of usual significance approach?
Oh, if we do just color?
Yeah, like in model where you had what was it, width and color?
Let's put color in there. Let's just put color in there right now. Cool. Boom. Fit. Summary. So if one decided to fit a simple logistic regression with color alone as a linear trend, then it would not be significant. I lied. It would be significant.
Interesting.
Yeah. So I guess a couple thoughts. There's 173 observations, which by logistic regression standards is not a huge number, a huge sample size. But you know, if you're curious about the p-value, color alone, its linear trend would have a significant effect. It's possibly to their advantage that the colors are well spread out, right? So if you think of this is not a design problem, but we know that terms with a good spread next are going to get more power. And I guess one thing you might say about color that's kind of nice is it's well spread out in its range. Good number of crabs from all the different colors, both categories. So that probably helps. Little intuition. And then there was another question in the chat. I can find it. Can different features be used in the models for this Bayesian model averaging? Oh yeah, and so the question is, could I have done this again with different features? I'm glad you asked that. Let's try one real quick with if we try to get rid of the watch this. Let's now get rid of one of the collinear terms and see what happens. So I'm going to say weight plus color plus spine. Weight and width. Let's do width and color and spine. Let's do weight and color and spine. We know that weight and width are especially collinear. So the question is, what happens if you get rid of a collinear term? Like that's what we like to do for other models. It's like, I mean, if you don't know anything about the subject-related material, but you like small standard errors and you're looking at it as a statistician, you're like, hey, I might be tempted to throw out a collinear X because then I get a story I can tell a little bit better. Let's see what would happen if we did that. There is my, I just ran the MCMC that fast again with only 3. So now I should have only 8 models. And let me get my graph here. And of course, it's going to do basically what your intuition expects. Those collinear terms that were looking equivocal are now going to look like dynamite. So I can't say anything about width because it's not a candidate anymore, but weight alone has now got like an 80% inclusion probability, right? So sort of as you'd expect, if your intuition from regular linear modeling is that introducing collinear terms destabilizes that coefficients and leads to big standard errors, and then you don't really know what's going on, but then you take some collinear terms out, and now all of a sudden the model seems very clear about among those terms that remain what their roles are. Same thing in model averaging. I removed width, which is highly collinear with weight. Before weight had like a 40% inclusion probability. Now it has like an 80% inclusion probability. So you could mess around with the code some more and look at their posteriors and that sort of thing. I did have 1 or 2 other slides I ought to get to. So this is like the moment in the talk where we're saying, even though this seems really cool, should we only do always this? And it's this great thing with no drawbacks. Unfortunately, no. No statistical technique is like that. And frankly, I think we're all getting a little bit tired of people who maybe hate an entire set of statistical techniques, and then they present some other set of techniques as if they don't have any drawbacks. I don't want to be this way. Here's the things to not like about Bayesian model averaging. Here's some downsides. First off, as elegant as it is, and as much as I like to use it, and it's been helpful for me to use it at times in my career, it tacitly assumes the true models in the candidate set. We call that M closed, right? So basically what we said is preposterous. We said, I'm trying to decide which of 16 models describe whether a female crab is going to have more potential mates. And I really think the true model's in the set. That's while this is a useful technique to perform inference and get intuition, it's not true that the true model's in the set almost ever, right? So the M closed assumption means I'm assuming that the true model's in the set. Bayesian model averaging assumes that kind of quietly. The M open means what happens if the true model is not in the set. In that case, that brings you to the second slide. There's this great paper by Yale, Vetri, Andrew Gilman, and I think one other person from 2018, Bayesian analysis. This was the discussion paper, great paper. It talks about this technique called stacking, and it points out Bayesian model averaging, as n goes up, we had small n here, we had 173. But if your n goes up, then Bayesian model averaging, it concentrates the posterior model probability on a single model, right? Which in M, if you're in M closed world, where you have the true model in your set, which you never do, and you're putting all the probability on the true model, that sounds awesome. But as pointed out in this paper, if you're in the M open, the more realistic situation where the true model is not in the set, now because I have a big sample size, I'm like 100% posterior probability of a certain model, we know that's not really right either. So a downside of Bayesian model averaging is as n goes up, it tends to put all the probability, more and more of the probability, functionally all of it on a single model, which then, like, what's the point of averaging? Because you just kind of put all the weight on the best model and you basically just did model selection, right? So you entered into this exercise to avoid model selection, but because your n was big, you have all your posterior probability basically on one model, and you sort of just did model selection anyways. So that's a drawback of that for sure. And it's one that we shouldn't pretend doesn't exist. More on this paper. There's this idea of stacking from the point estimation literature, but the basic idea is for Bayesian model averaging, I use posterior model probability as the weight to weigh different models. Well, if you instead for the weight, if you basically use some measure of ability to predict out of sample data, that's the big idea behind stacking. Choose model weights based on how well each model predicts new data. That's the broad idea. There's a lot to it, but that's the broad idea. And if you do something like that, then it tends to be even better for out of sample prediction. And it tends to not concentrate all of the probability on a single model the same way BMA does. So that paper is worth a look at. If you're in a situation where you've got so much data, Bayesian model averaging is only picking a single model, you might consider stacking as an alternative. And by the way, these are much bigger things than just categorical data analysis too. In fact, as I recall, this paper about stacking, everything it says about BMA is correct, but I think it focuses mostly on continuous outcomes. So that's something to bear in mind as well. So those are some downsides. Very elegant, very cool, very helpful, but it quietly pretends something that isn't true is true, that we have the true model on our set. And as n goes up, it's going to put a lot of weight on a small number of models, which might or might not be what you wanted. References, 3 pages of them. I chose these references because coming out of grad school with only like a little bit of experience in Bayesian statistics, I found these to be the papers that helped me like up my game, right? These ideas are older than most of these papers. So I'm just saying, these are like recommended reading references. And you could probably look at most of this stuff and say, well, there's some earlier version of the thing too. That's true. So I leaned more towards those references for this demonstration to point you towards papers that I thought were readable and accessible and relevant. And I guess I'm just kind of hanging around to see if there's any questions. Here's one from Eugene Gallagher. I don't have Agresti 2nd edition. I have Agresti 1996, the 1st edition. Oh yeah, I do too. It's crab data and selection model using deviance, including width and color as the predictors. Yeah, so, I think I have that book also. 2004, George Terrell taught me categorical data analysis, an introduction to categorical data analysis. This is oh, by the way, this is how you do an update, right? This is what I learned from in 2004. It's skinny, easy to carry around. Here's the 2018 version. This 3rd edition is for real. It's got like more modern stuff in it. It talks less about contingency tables, more about modeling. It talks about classifiers, some smoothing in there, I think more on mixed models. So since the topic of earlier editions of some of Alan Agresti's books come up, these are some meaty updates between editions. I don't have the 2nd edition, but the crab data is older than the 3rd edition. That's a good point. In terms of deviance, basically deviance is likelihood ratios against saturated models. So whatever you conclude with deviance is basically what you might have gotten if you used likelihood ratio tests. But again, we can leverage all 16 models sensibly with model averaging rather than just having to pick one. I'll elaborate a little more at this deviance. Deviance, let's see if I can remember this. Deviance is twice the difference in log likelihood between the saturated model, which is the biggest possible model based on how you arranged your x's, from the model under consideration. Right. So if you take the difference of 2 deviance scores, the log likelihood term based on the saturated model cancels out, and you're left with a likelihood ratio test statistic.
If anyone wants to reach out to you outside of here, if you're okay with that.
Oh yeah, I'd be happy for people to contact me if they want to talk more about this stuff.
Well, perfect. If there isn't anything else, I'd like to thank our speaker again and wish everyone great summer, and hopefully we'll see you at JSM.